Today we are going to test the synthesis of uranium tetrafluoride using various reducing agents. I've specifically chosen 3 particular reducing agents. There are many more suitable reducing agents for the uranium tetrafluoride synthesis though. But first, why use reducing agents and why should we make uranium tetrafluoride in the first place? In solution, uranium is the most stable at the oxidation state of +6 and +4. The other oxidation states are also known, but from all of them, hexavalent uranium is the most stable chemical form in an aqueous solution. It exists as the uranyl ion, and all of our highly water-soluble chemicals also contain the uranium in the +6 oxidation state. We have uranyl acetate and uranyl nitrate hexahydrate here in the lab. To produce uranium tetrafluoride, you must therefore add 2 electrons to the uranium atom. This is done using a reducing agent. Subsequently, by adding fluoride ion, one can obtain a solid that contains uranium 4+. As a solid, uranium 4+ is also quite stable. So why of all the things do we need uranium tetrafluoride? It is classically known in the context of uranium enrichment. According to this scheme, uranium tetrafluoride is used to produce volatile uranium hexafluoride. There are a few other ways to produce uranium hexafluoride. Sometimes uranium tetrafluoride is also used to produce metallic uranium, but tetrafluoride isn't strictly necessary for this. It can also be done using the dioxide, for example. I just wanted to experiment a bit because on paper gaining 2 electrons is easier said than done. Please never attempt the nuclear chemistry experiments shown here outside of a specialized laboratory. This video is for educational purposes only. Uranium and hydrofluoric acid are extremely dangerous, and mishandling these chemicals is unfortunately very easy. So do not try this outside a professional lab. And let's weigh out our chemicals. 0.5 grams of uranyl nitrate hexahydrate equivalent to approximately 1 millimole is weighed out. Since I'm doing 3 runs, I'm weighing out exactly 4 batches, the 4th one being for a YouTube short. So, uranyl nitrate is the nuclear chemistry component, right? I mean, poisonous green, radioactive, and it sparkles beautifully. In addition, for each batch, we need copper sulfate as a catalyst for the reduction. We weigh out 0.03 grams of the pentahydrate. The first reducing agent is sodium borohydride. According to this reaction, it can be seen that theoretically 1/4 millimole would be needed. That amounts to 0.01 grams, so we'll weigh that out first. The next reducing agent is L-ascorbic acid, better known as vitamin C. From the reaction equation, we can see that uranyl reacts with L-ascorbic acid in a 1:1 ratio. To obtain 1 millimole of L-ascorbic acid, 0.176 grams is required. And last but not least, sodium formiate is used. Here too, according to the reaction equation, the ratio is 1:1 and 0.068 grams is needed. I'll go into this again later in the theory section. Here's an overview of all the chemicals used. Okay, I just wanted an excuse to include even more shots of the beautiful uranyl nitrate hexahydrate. L-ascorbic acid and sodium formiate can be prepared as a solution in a small amount of water. Since we are going to work with warm, concentrated hydrofluoric acid shortly, only Teflon is suitable as a reaction vessel. The uranyl nitrate is added to it alongside with the copper sulfate pentahydrate. I've also read that in addition to copper ions, chloride ions are also needed for this reduction to proceed well. So this mixture is then dissolved in 4 milliliters of 4 molar hydrochloric acid. 4 molar was simply a compromise of it's readily available in our lab and contains chloride ions. Now I put on some heavy duty gloves because concentrated hydrofluoric acid is being taken out of the cabinet. Whenever working with concentrated hydrofluoric acid, it is mandatory to have calcium gluconate ointment on hand. Calcium gluconate is really for minimizing damage. It is applied on the affected area where the calcium is supposed to convert the fluoride ions into insoluble calcium fluoride. This disclaimer is far too short, but this also isn't just a tutorial to try at home anyways. The 0.5 milliliters of 40% hydrofluoric acid is added, and this contains approximately 110 millimoles. 40% hydrofluoric acid has a concentration of 23 moles per liter. We need 4 times the amount of fluoride ions, and this is far more than enough. An excess of hydrofluoric acid, and from now on everything that has come into contact with HF is neutralized with a supersaturated calcium hydroxide solution. I'll always find 80 degrees C to be a pretty comfortable temperature. Yes, that's the temperature measured in the Erlenmeyer flask, and the thermal conductivity of Teflon and glass is different, but I still need my temperature probe, so no hydrofluoric acid for this probe. Honestly, as long as it's warm. After 5 minutes at elevated temperature, the reducing agent is now added drop by drop. Nothing happens with the L-ascorbic acid at first. But in the next shot, where I wanted to add the sodium borohydride solution, you can definitely see a color change in the L-ascorbic acid vessel. When borohydride is added to acid, a gas is naturally produced. Hydrogen gas. And you can see upon contact an orange, brown, reddish color forms that disappears quite quickly. And that's so cool, and I will explain why I find that so cool in the theory section. Any guesses? Now the sodium formiate is added. After a reaction time of 15 minutes, the whole thing looks something like this. So, how do I best explain that now? Let's start with the L-ascorbic acid. So, the reaction with the L-ascorbic acid shows the desired color change. So there's no need to worry about that. What happens here, L-ascorbic acid does not directly reduce the uranium in the uranyl ion, but instead it reduces the divalent copper from the copper sulfate to monovalent copper. And this monovalent copper ultimately reduces the uranium according to this reaction. That means you add copper ions to enable the reduction of uranium with another reducing agents that can't directly reduce the uranium. Copper is not consumed in this case, so it's a catalyst. So you could also firstly dissolve the copper in hydrochloric acid and then reduce it with L-ascorbic acid and then add the uranium later. That would result in several beautiful color changes. With the sodium formiate, absolutely nothing happened. Why should anything happen here at all? Sodium formiate in hydrochloric acid forms formic acid. Formic acid is known as a reducing agent. The mechanism behind the reduction varies depending on the application. It contains carbon in the oxidation state of +2, which theoretically can be oxidized to CO2 with the carbon in the +4 oxidation state. However, what actually happens is that formic acid is decomposed into carbon monoxide and water, and then this carbon monoxide acts as a reducing agent. You can also see a reduction of hexavalent uranium using pure carbon monoxide gas on Wheeler Scientific's YouTube channel. However, this decomposition of formic acid only occurs in highly hygroscopic agents such as concentrated sulfuric acid. These conditions do not apply to our system. Carbon too can reduce uranium, just not in the form of plain old sodium formiate in aqueous solution. Accordingly, I added L-ascorbic acid to ultimately extract uranium tetrafluoride from this as well. These sodium ions will also cause us some problems, but I'll get to that when evaluating the PXRD data. Now onto the borohydride. Here we have the hydride ions with a very strong reducing potential. Put simply, hydrogen is produced and can act as a reducing agent according to this reaction equation. As I already hinted during the weighing, sure, theoretically a 1:4 ratio would be sufficient, but as you can see, quite a bit is bubbling out. So off camera I slowly added more until the solution visibly cleared up. The red stuff we have seen here is most likely trivalent uranium. In this image from Los Alamos lab, it looks like trivalent uranium in solution produces a dark blue color. On the website itself, it's described as being dark green to dark red depending on the light source. And uranium trifluoride is also described as a red solid. Here it's only stable in this highly reducing form of hydrogen gas. As soon as the strong reducing effect dissipates, the trivalent uranium oxidizes to the tetravalent uranium. Of course, I had to push the limit again, and if I go a bit overboard with the addition, you can see a purple tint. I would guess that these aren't other oxidation states of uranium, but rather either a color overlap, nanoparticles, or reactive uranium oxyfluoride species. But that's just a guess. If you know more, please let me know. In any case, with sodium borohydride, you can't rely on stoichiometry when weighing it in. Instead, you have to keep in mind that the reducing agent is gaseous. These suspensions were left to cool and then filtered. The filtrate contained fluoride and therefore was added dropwise to calcium hydroxide solution. The residue was washed several times with distilled water and then dried in a desiccator for 3 days. I have to be honest, I'd admit that I didn't determine the yield. Instead, I used it directly for some other synthesis. So what exactly did I produce? The linked paper I referred to describes uranium tetrafluoride 3/4 hydrate. With sodium formiate, I expect contamination of NaUF5. This apparently is quite a common impurity when sodium or ammonium ions are present. X-ray powder diffraction was used for analysis. and the following results were obtained. The use of sodium borohydrate led to the formation of beta-sodium pentafluorouranate monohydrate. In the experimental setup with sodium formiate, to which I added L-ascorbic acid afterwards, sodium pentafluorouranate monohydrate was also formed. The experimental setup using only L-ascorbic acid as an electron donor led to the formation of uranium tetrafluoride X hydrate. X in this case is either 1.5 or 2. The following are key insights to be drawn from this synthesis of uranium tetrafluoride in an aqueous solution. The presence of sodium leads to the formation of a double salt, sodium pentafluorouranate. Alternatively, at elevated sodium ion concentrations, the disodium hexafluorouranate may form. Formally, this is a double salt of sodium fluoride and uranium tetrafluoride. Visually, they all look extremely similar, and without instrumental analysis, one cannot simply claim to have produced uranium tetrafluoride. Especially not if you have purified the uranium yourself from its ore, because there's a lot of sodium contained. However, I suspect that for the two applications mentioned at the beginning, it makes little difference whether it's the double salt or not. Furthermore, it's important to note that this process never yields anhydrous uranium tetrafluoride. Anhydrous uranium tetrafluoride also looks quite different visually. It has a much more vivid green color and not such a pale green. Most images, including the one I showed here, depict the hydrated uranium tetrafluoride because its synthesis is so much easier than that of anhydrous uranium tetrafluoride. Hopefully, this has given us a few insights into basic chemistry of uranium. There is much more you can do with tetravalent uranium besides simply precipitating it as a fluoride, but these would be other exciting syntheses that we can carry out here at the university. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye!